Welcome to this video where we'll be looking at the answer to the idea of the charge distribution between the uneven surfaces. So at the end of the last video, I left you with this challenge, and the challenge was to figure out what would happen with the total charge of the system evenly distribute between the two spheres if they were connected with a conducting wire if radius 1 was 4 times radius 2. Well, the answer is that they would not be the same at the end. And if you think back to Coulomb's law and you think about the idea that we've been talking about the entire time, the relationship between the electrostatic force and the distance between the charges is this inverse squared relationship. And so that it wouldn't be the same as, let's say, if I had 4 charges on this big one, that would not be the same as having 4 charges on this one, because in this case, these are a lot closer together than these are, and so the situation would be very unbalanced, and this would not be the best configuration to achieve. So what we're going to do is take a look at a new concept or a different concept that relates the two together, and we won't give an exact answer today of when the flow of charge will stop, but we will discuss a method to solving it and to understanding it. So if you look down here at the bottom, I have this concept of charge density written up. And we talk about linear charge density, surface charge density, and volume charge density. Because it's not just the total charge that affects the nature of the object, but it's actually how the charge is distributed. Now, linear charge density, of course, is just one-dimensional. So this is how we're looking at if we had a one-dimensional metal rod, let's say, we're looking at how the charge is distributed through that metal rod. And so we use the Greek letter lambda to represent linear charge density, and that's equal to the amount of charge per unit of length, which would be the same thing as mass density, as the amount of mass per unit of length. So I'm going to rearrange this to write the total amount of charge on the object would be equal to the density times the length. Similarly, with surface charge density, that's a two-dimensional consideration. This is where I would have maybe a two-dimensional surface where I would have the charge distributed on the surface. This we use the Greek letter sigma, which is equal to the amount of charge per unit of area. So the charge total could be then just written as sigma times A. The volume charge density, of course, could be if we had a volume shape where the charge was distributed throughout the volume of the object, and this would be using the Greek letter rho, which is equal to the amount of charge per unit of volume. And then, similarly to the others, I would have the total charge is equal to the density times the volume. So when we're trying to compare these two and to figure out how much charge would be in one place than the other, what we might first do is estimate it. Which one do we think could hold more charge? Well, obviously the big one will hold more charge than the small one will, just by sheer amount of space. But to figure out the proportion of the amount of charge that could be here versus here, which would stop the flow of charge, we're going to learn a more elegant way to do that in subsequent videos. But what we'll do first here is say maybe the charge densities of both of these are the same. In other words, if we call this one sigma 1 and this one sigma 2, we would say that, okay, maybe they have the same distribution per unit of area, because remember, this is on the surface of the sphere, which is the surface area. Now what I could say is, let's figure out the amount of charge on object 1 to the amount of charge on object 2. And what we might do there is substitute in the expression that we just came up with over here and say that that's equal to sigma 1 times area 1 over sigma 2 times area 2. Now if we said the sigmas are the same, those would factor out, and I'm going to write the surface area of each sphere into this. So I'll do Q1 is equal to, so Q1 over Q2, sorry that was redundant, would do is 4 pi r squared. And then for this one, again, the area is 4 pi r2 squared. And so if the 4 pi's cancel out here, we see that the ratio of the charge on object or sphere 1 to the charge on sphere 2 is proportional to the ratios of the radii. So you can see there very similarly, this would be just like having fractions where we would have maybe 100 over 10 is the same thing as 10 over 1. And so you can see that the charge would distribute in such a way that is proportional to the radii of the two objects. Now that's an important concept, the idea of charge density, but it is going to become more important in AP Physics C than it does in AP Physics 2 because of the fact that the charge density in AP Physics 2 will almost always be or will always be uniform, whereas in AP Physics C it may not be. So for the next video, what we're going to do is we're going to talk about why that is. Why is it that you can have more charge here than here and it stay at a state of equilibrium? And it has to do with the concept of energy. And so I'm going to leave you with the challenge that I do every time. And this challenge is, I want you to think about in terms of energy. So in terms of energy, why is it different having 4 charges spaced evenly over this large radius versus 4 charges spaced evenly over the small radius? What is the difference in the energy configuration? So I'll say the energy configuration here versus the energy configuration in this case. Try to come up with something that relates the two to each other.